time for us to talk about using the basic divergence test, also known as the nth term test, and the integral test, where our basic question becomes, hey, at the end of the process, is what we're going to get a number, or is it hopeless? So we're not actually after finding the value, because most of the sums we talk about, forget it, hopeless. But we can at least say, hey, if it were possible to add all these things up, do we end up with a number? That's what we want to do. Now, this is kind of an interesting transition because we're so used to be like, okay, find the number. And now we're switching to yes, no questions. Does it converge? Does it not converge? And it kind of makes it feel a little bit uncomfortable. It feels a little bit more fuzzy. So what does that mean? It means that you've got to learn to be more comfortable, and that means practice. The more that you practice, the more comfortable you get using these tools. So do as much practice as you can. If you're following along, make use of the pause button. See a problem that you like, pause. Try it out yourself first and see how you do. If you need help, I'm here. Just unpause. Life is good. Well, let's begin. Our first problem. What can be said about the following series using the nth term test? So, what do? Well, we look at the nth term. Now remember, what does the nth term test say? It says, do the terms go to 0? And the answer is no. Forget it. Just stop. Doesn't converge. Now, what happens? Well, what are the nth terms? So here, the question is, what happens to this? Well, this term, we see, look, it's heading towards infinity. So it's definitely not going to 0. And so we can say, look, doesn't converge. Now, if we wanted to, we could say, look, it's actually even stronger than it doesn't converge. Because when we say it doesn't converge, it means it doesn't converge to a finite number. But we could say justifiably, hey, this is going to be infinite, because if you add it up, it just keeps growing. And in fact, the terms get bigger and bigger as you go on. Now, if you go online and watch certain videos, you'll see, oh, this is actually like something like -1/12. No, forget that. No. That's a different kind of mathematics. It's not the math we're doing. So here, if you add up all the numbers, you're going to get something infinite. Now, how about our next term? Well, -1 to the n. What's happening to those? Well, it's going to 1 or -1. It actually oscillates, right? You see 1, -1, 1, -1, 1, -1. And that's not 0. And so it doesn't converge. That's what the test says. See, the test says if it doesn't go to 0, it doesn't converge. And you'll notice here what's happening. Well, if you look, you can look at the partial sums. So if we just start by covering things up, it says, look, initially our partial sum is just 1. And then the next term we'll get 0. And then back to 1. And then back to 0. And back to 1. And back to 0. So actually the partial sums look like 1, 0, 1, 0, 1, 0. You might say, hey, what is that? No, it's not a half. It just says the partial sums keep jumping back and forth. It never settles down on anything. So when we're talking about a sum of a series, we're saying, hey, the partial sums, they're settling down on something. Here it doesn't happen, doesn't converge. All right, now the last one, -1/2 to the n. And we say, well, what happens to that? It goes to 0. What's our conclusion? The conclusion is we don't know. Because remember, what are we doing here? We're using the nth term test. The nth term test is not a test that says something will converge. It's a test that says, oh, if a certain situation holds, you don't converge. But it can be the case that the terms could go to 0 and you still don't converge. We've seen examples of that. So when the terms go to 0, the test is sort of inconclusive. Try again. Of course, in this case, we can make progress. It's not so hard to see, oh, this is a geometric series. It does converge. But that's not by the nth term test. And the question is, what does the nth term test say? And so for us, it's inconclusive, just from the test. Well, the good news is we're going to develop more tools. There will be more tools, better tools, and of course, even with all the tools we have, there will still be problems about we can't do. Well, just means better tools to learn about in the future, right? Yeah, it's always nice to say, good, our learning isn't done. More yet to do. Okay, well, let's look at the following. Determine whether the sum from 5 to infinity of n sine 1 over n converges. Now, there's a little bit of like a, what, 5? What? But here's the thing. We don't care where we start. Whenever we're talking about convergence of a sum, it's not where you start, it's how you end. It's probably the same in college, right? Look, it's not how you do in your first semester or second semester. It's how you finish. So don't worry too much and stress over how you're starting your college career. Say, look, finish strong. Now for us, when we say we care about where we finish, we mean way down there. We're looking way down where the tail of the series is. In other words, the terms close to infinity. Now, we have sort of two tools. One is the integral test, and the other one is our nth term test. Let's use the nth term test. Now, the nice thing about the nth term test is it's very simple. The bad thing is, because it's simple, it's a little weak. But when it works wonders. So we ask ourselves the question, what happens to n sine 1 over n as n goes to infinity? So that's our question. What does that do? Now, if you notice, we say, hey, we can write that as the limit as n goes to infinity. We can put the n downstairs as a 1 over n. Sine of 1 over n divided by 1 over n. And now you might say, well, why were you doing that? Probably we should have motivated before why we did that. If you think about what's currently happening, n is getting big, so that's going to infinity. 1 over n is getting small, it's going to 0, and sine of 0 is 0. So you have infinity times 0, which we all know that infinity times 0 equals more work. More work. There's still stuff to figure out. So we're setting it up. Now at this stage you have two options. One is you say, hey, I know what's happening. And the other one is, le Hopital. Now, we'll do le Hopital first. Then we'll say, wait a second, we should have seen it before. Because what do you see? It's going to 0 over 0, right? And say, all right, since it's going to 0 over 0, apply le Hopital, and let's see what we get. So this is equal to, according to the rule, limit n goes to infinity. And, use the chain rule. And n is our variable here. Derivative of sine is cosine 1 over n times the root of the inside minus 1 over n squared. Downstairs, 1 over n minus 1 over n squared. And now we're like, wow, amazing, amazing. The minus 1 over n squareds cancel. So it's like cosine 1 over n. Well, 1 over n goes to 0. This goes to cosine 0, which is 1. Great. Now, let's finish our problem, then we'll talk about, we should have seen that. What's happening? This says that the terms, the individual terms here, are going towards 1. That's what we've just shown. So when we're looking at our sum, our terms, as we get further and further down, as we move closer and closer to the end, they're getting close to 1. So as we move towards the tail, it looks like plus 1, plus 1, plus 1, plus 1, plus 1, plus 1. Terms don't go to 0. Therefore, we know it doesn't converge. We can be slightly stronger and say, hey, it actually diverges to infinity because you're always adding on something more. But for us, we can say it diverges. That's the answer. Now, I said, there was something else we could have said, and that is, look, we have sine of 1 over n over n. And there's this basic fact from Calc 1, and even doesn't really use calc tools, but it says sine of blah over blah, if you're taking a limit of blah going to 0, is 1. You're like saying, wow, blah, what is that? It's just a standard for saying something, right? We don't want to get too caught up that says, oh, it has to be x, it has to be, no. It's just sine of something over the same something downstairs. If we see that, like, hey, if our pieces are going to 0, we know that approaches 1. So in here, 1 over n, that's our blah. And indeed, 1 over n does go to 0. So we said, that's like sine x over x, it goes to 1. Okay. Well, that wasn't so bad. Well, because it was a pretty, in some sense, bad series, right? Because terms weren't going to 0. All right. Well, now, here we go. Some other questions. Does the sum of 1 over n squared plus 1 converge? And how about 2n over n squared plus 1? Does that converge? Now, let's just apply our nth term test, our basic divergence test, and say, do the terms go to 0? Well, yeah, 1 over something squared. And that's getting huge. And here, yeah, it's also going to 0, right? Because look at the degree. The degree downstairs is larger. It's going to dominate. So, our basic divergence test tells us nothing. We have no clue whether or not it converges or diverges. So, all right, can't use that test. And the good news is we haven't learned very many tests at this point. So by process of elimination, let's switch over and do integral tests. Now, we can say, well, let's look at the integral. So think of this as the integral 0 to infinity of 1 over x squared plus 1. And we'll work that integral out. And then here, you might say, okay, integral 0 to infinity of 2x over x squared plus 1. And we'll work that one out. And the integral test says, hey, the sum is linked to the integral, as long as a couple of conditions are satisfied. So let's briefly talk about the conditions. Should have a reasonable function, which is continuous, positive, and going to 0. Yeah, continuous, positive goes to 0. Now you might say, see, okay, that one isn't quite right, because what happens is it starts at 0, goes up, and then goes back down. Shouldn't we be worried about that little part that breaks the rule? And the answer is no, because we care about the tail. And the long-term behavior of 2x over x squared plus 1 says, I'm a function that goes down where I need to be going down. So we're okay. Well, all right, this is not so bad. That's arctangent of x. And going from 0 to infinity. Now, of course, whenever you have infinity in the balance, there's a limit here. And sometimes we write the limit, sometimes we don't. It just depends on whether or not it's something that we really need to pay more attention to. So when we plug in infinity, really means as we go to infinity, what happens? Arctangent goes to its asymptote, goes to pi over 2. So what we end up with is pi over 2. Now the important thing is, this is finite. Now that does not say that sum is pi over 2, because it is definitely not. And it is known what the sum is. We don't have the tools to do it using our technology, but the sum is known, and it is not pi over 2. But that's not what the integral test tells us. What the integral test tells us is it says, hey, this is what you have to pay attention to, whether it's finite or not, because they're tied together. So our conclusion is that the sum from 0 to infinity of 1 over n squared plus 1 converges. All right, great. Beautiful. Now, over here. 2x over x squared plus 1. Now you might notice, ooh, the derivative of x squared plus 1 is 2x. So it's the derivative on the top, function on the bottom. When you see that, derivative over function, you say, hey, that has a nice antiderivative. It's the log of what's downstairs. You can check it, right? Derivative of log of x squared plus 1. 1 over x squared plus 1, that gives you your denominator, times the derivative of x squared plus 1, which is 2x. Going from 0 to infinity. Now we do the same thing. In infinity, there's a sort of a built-in limit, because you can't plug in infinity. Infinity is not a number. But the question is, as we head off to infinity, what happens? Well, as x goes to infinity, x squared plus 1 gets bigger and bigger, grows without bound. So log of something growing without bound also grows without bound. This is infinite. So, also known as not finite. So it doesn't converge. And so what's our conclusion? Well, our real conclusion is, look, this integral doesn't converge. We can even say more, because what we've done is we've tied it together. If you look at the integral test, it says, hey, in some sense, I can bound the integral below by the sum and above by the sum, just shifting a couple of terms at the start. So if one of them is infinite, they're both infinite. So we could actually say this is infinity. So you could say not converging. Again, this comes down to the question of what do you mean by converging, diverging. If you say, oh, infinity is considered converging, that's great. If converging says, no, it has to be a finite number, then not converging. But either way, we know what's going on. Life is good. All right, great. Well, let's keep going. More to do, right? More to do. Okay, so let's do our next problem. For 0 less than r less than 1, show the summation of n r to the n converges. All right, well, this should be interesting. Now, one of the things you might say, why are you assuming r is positive here? We'll get into that. So what can we say? Well, all right, we want to show it converges, which means we can't use the nth term test. That's completely out. The nth term test never shows anything converges. The best it can do is show something diverges. But I can't come to the end and say, aha, I conclude that something converges. So we've got to be doing an integral test here. Okay, so we know coming in, integral test, that's our mindset coming in. So we say, okay, think about the function, integral 0 to infinity of x r to the x. And we want to think about, okay, can we integrate that? Now, what happens? Well, one thing to note is if you plot x r to the x, it starts at 0, but it does turn around and goes back towards 0 in the long run. Because if you think about what you have here is you have polynomial x versus exponential. Exponential beats polynomial, and the exponential part is going to 0, so it's going to go to 0. So the fact that we decrease in the long run says, okay, integral test makes a lot of sense here. We don't worry about what happens at the start. All right, well, why do we care about the fact that r is positive? Well, the thing is, if r is negative, what does it mean to have like a negative number to like weird values, like a negative to the half power? Uh-oh, that sounds complex. But you can imagine even stranger values, like, negative a half to the value pi? Like, what? What does that even mean? Well, it means something, but we don't have the tools to figure it out. So the fact that we're applying the integral test says, in order for us to apply, we have to have a function that we can work with, which says r has to be positive. Okay, so that's a good thing to know. One other fact, which we're going to make use of, and a nice recall back to the fun days of Calc 1. If we integrate r to the x dx, well, we know how to integrate e to the x. What we can do is we can say, well, look, r is the same as e to the log r to the x. And so this is really e to the log of r times x. And now we're like, okay, that we can handle. So what we end up with is when we integrate, well, it's e to the log r x divided by that log r. Or, because we know e to the log r of x is really r to the x, we could write this as 1 over log of r times r to the x. So just keep that in mind. Okay, well, here we go. All right, integral x times r to the x. Well, we're going to need to do parts here. Well, we'll let u be the x, dv r to the x dx. So du is dx, and v is 1 over log of r times r to the x. So we get uv. So this is 1 over log of r x r to the x. Okay, and go from 0 to infinity, and then minus integral of v du. And it's still 0 to infinity, by the way. And so 1 over log of r, r to the x. So we get 1 over log of r, x, r to the x, minus, and here we get 1 over log of r squared, r to the x, because you bring down another natural log of r. We need to integrate the second time and evaluate 0 to infinity. All right, great. Now, if you plug in 0, you'll get 0 in the first term. R to 0 is 1, so you end up with 1 over log of r squared. That's the real question is infinity. What happens as we go to infinity? Well, r is small. When we raise it to a large number, r to infinity goes to 0. So we say, aha, this part here goes to 0 as we go to infinity. Now, what about x, r to the x? It depends how comfortable you feel. Because you can say, look, I have the x polynomial, r to the x is exponential. Who wins? Well, r to the x wins. Exponential beats polynomial. And I know it's going to 0, and therefore I could say with confidence this goes to 0. Now, what that ends up telling us is like, okay, as we go to infinity, we got 0. When we plug in 0, this term is 0. So the only thing that's left ends up being this one piece here. And because we subtract when we plug in 0, we get 1 over natural log of r squared, which, by the way, is finite. Okay, let's finish the problem and do the scenario. What if we're not comfortable? Well, okay, so what's our conclusion? Well, integral being finite, and the integral test says, hey, if the integral is finite, the sum is finite, and vice versa. And so our conclusion is that the sum, n equals 0 to infinity, n r to the n, is also finite. In other words, converges. And we're good. Okay, so that's the end of the problem. Now, what if you aren't comfortable with the fact that x, r to the x goes to 0? Well, no problem. You can think of a limit as x tends to infinity, and I'll write x r to the x as x, and r to the x I'll write as r to the minus x. So in other words, I'm just rewriting it as a ratio. And now what happens is you see, this goes to infinity over infinity. Apply L'Hopital. Aha, L'Hopital. And we get this as the limit as x goes to infinity. we'll end up with a x. The root of x is 1. The root of r to the minus x is r to the minus x times natural log of r, because of that r base, similar process to what you did over here, times by a chain rule minus 1. And now we say, look, top is going to 1, bottom still is huge. So it goes to 0, which is what we need. All right. And so we're done. So yeah, the sum converges. We don't know what it converges to, but we do know it converges. So woohoo, good for us. All right, great. So for the next problem, let's actually find the sum. What? We just said we don't know what the sum is. Okay. So we're going to do it. We're going to do it. And I want to preface this by saying what we're about to do is, I don't want to call it a trick, but it's something a little bit different than what we've done so far. Because this is not a sum that falls into the category of being telescoping. There's no way to rewrite it as, oh, something minus something that's been offset. And it's not geometric. Can you see why? Well, look, you have r to the n. That's definitely geometric. The problem is that there's this extra n there. And so that's why it's not geometric. But it's almost geometric. And that's what we're going to be using, the fact that it's almost geometric. So let's think of what this sum looks like. Well, when we plug in n equals 0, we don't have anything. We have 0. So let's really start with 1. So I'm going to think of this as 1 times r plus n equals 2, 2 times r squared. N equals 3, 3 times r cubed. Then 4 times r to the 4th. And 5 times r to the 5th. And I think by now you see, yeah, that's what it is. So what do we do? So we're going to break things up. So what do we mean? Well, look, when I think of 2r squared, it's like that says there's 2 copies of r squared. So I'm going to make 2 of them. So I'm going to say, okay, I have an r, and then I have an r squared. It's like, oh, well, there's another copy of r squared. Okay, so I'll put that underneath. R cubed, there's 3 of them. So I'll make 3 copies of it. There's an r cubed. I'll put an r cubed here, and I'll put an r cubed there. R to the 4th, 4r to the 4th. So it's r to the 4th, r to the 4th, r to the 4th, and r to the 4th. And you can see, there's just really breaking things up into lots and lots of pieces. And now at this point, you're like, wow. So instead of just one sum with infinitely many terms, now you're going to end up with a lot of sums with infinitely many terms. In fact, you're going to end up with infinitely many sums, right? So there's that first sum, then there's the second sum, and so forth and so on. And now you're like, wow, great. Kind of hopeless, isn't it? No. There's hope. There's definitely hope. So where's the hope? Well, notice that each one of these things is what? Every single sum that we have is actually really nice. Look at the first one. R squared, r cubed. It's geometric. So that first sum becomes equal to what? Well, if it's geometric, it's the first term, r, divided by 1 minus what you multiply by. 1 minus r. Okay, how about this second sum? Well, that would be the first term, r squared, divided by what you multiply by. And see, notice we keep multiplying by r. R times r times r times r. So, again, by 1 minus r. The third row, we add those up with first term, r cubed. And every time we multiply by 1 minus r. And you see the pattern continues. And so forth and so on. So what we come to the conclusion is, lo and behold, our original sum, when we break things into lots and lots of pieces and rearrange and combine, we saw, oh, we can really use tons and tons of geometric series and say this is equal to r over 1 minus r plus r squared over 1 minus r plus r cubed over 1 minus r, and so forth and so on. And here, we did use the fact that r is small because we're doing geometric sums, but we still have infinitely many terms we're adding up, right? Except, what kind of sum do you see? It's geometric. To get from the first to the second, you multiply by r. From the second to the third, multiply by r. Third to the fourth, multiply by r. So we say, aha, if it's geometric, you take the first term, so that's r, divide by 1 minus r, divide by, what are you multiplying by? At every stage, we multiply by r, so divide by 1 minus r. So our conclusion is, this is r over 1 minus r squared. And we're done. It's kind of a lovely answer. It's beautiful. Now, you might say, wow, could we have done this in a different way? And I'll tell you, we will. We will come back and do a problem essentially like this later on when we have better tools. And we'll see, it's going to be beautiful. It's going to be really kind of amazing. Now, in some sense, as foreshadow of things to come, you might say, hey, if I took the derivative of 1 over 1 minus x, it's really, really close to what I see here, because the derivative of 1 over 1 minus x is 1 over 1 minus x squared. Almost what you see here. That's a good thought to have. As I said, we will come back and do this problem again in the future. So be ready. It's coming. It's coming. All right. Well, let's try another problem. All right. Suppose that a sub n, n equals 0 to infinity, it's 1 over 1, 3 over 2, 5 over 4, 7 over 8, 9 over 16, 11 over 32, so forth and so on, where the numerators are odd numbers and the denominators are the powers of 2. And what's the question? Find the sum of a sub n. Okay, and it says, hey, there's a hint. We just did this one. All right, the sum n equals 0 to infinity, n r to the n, r over 1 minus r squared. Yeah, that's true. We know it. Great. So, how do we do this? Well, let's think about what's going on here. First off, what is a sub n? We have it listed, but what we'd really like is we'd like to have this as a function of n. In other words, we have right now sort of a description. We can speak out loud. Oh, it's the odd numbers divided by powers of 2, but we'd like to be more precise. So let's do our denominators. So if we start here, this is the 0th term, n equals 0, n equals 1, n equals 2, so forth and so on. So it's 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. So our denominator is 2 to the n. What's our numerator? Well, 1, 3, 5, 7, 9. Okay, so how do we rewrite that? Well, odd numbers, it looks like 2 times something plus 1. Every odd number has that form. 2 times a value plus 1. So that's like 2 times 0 plus 1, 2 times 1 plus 1, 2 times 2 plus 1, 2 times 3 plus 1. Okay, so the numerator looks like 2 times n plus 1. Okay, this is good. Now that we have a formula, we can start thinking about our sum. So our sum, n equals 0 to infinity of a sub n, it's really the sum 2n plus 1 over 2 to the n. Now, we have to be careful here. It's not that, not yet. But what can we do? One thing we can do is we can make use of the plus sign. See, there's this plus up here in the numerator. And that says you can break up over addition. So one thing we can do is let's pull it apart into pieces. And if we do that, we say, look, I can pull that apart. I can even bring the 2 out. So this is 2 sum n equals 0 to infinity of n over 2 to the n. That's the first piece, plus the sum n equals 0 to infinity of 1 over 2 to the n. Now, let's just do one more step. We really like to have things written in our form for exponentials, so something to the n power. So just to make it unambiguous here, I'm going to rewrite it as n 1/2 to the n. And again, sum 0 to infinity 1/2 to the n. And now we're like, perfect. Perfect. Because what can we do? Well, we see the first term, it's exactly the right form. N r to the n. And where r is 1/2. So according to the rule, it's going to be 1/2, which is r, over 1 minus 1/2 squared. How about here? Well, that's geometric. What's the first term? Plug in 0. 1/2 to the 0 is 1 over 1 minus 1/2, 1 minus r. And we say, okay, well, 2 times 1/2 is 1. 1 minus 1/2 is 1/2. Squared is 1/4. That's downstairs. Flip it over. We'll make it the first term equal to 4. 1 minus 1/2, that's 1/2 downstairs. Flip it over. Makes it 2. And therefore, we come to the conclusion 4 plus 2, which is 6. And there we go. We're done. Aha! Good. Well, that's because, we add certain terms. And of course, there's a little bit of like, ooh, we can break things apart. All right, good. Well, I think we have time for one last problem. One more. And this one's going to be a little bit different. Actually, it's going to feel a lot different. So, here we go. Use the integral test to determine how many terms are needed to approximate the sum of the series, sum k equals 1 to infinity, 1 over k squared plus 1, with an error less than 10 to the negative 5. Okay. All right. We need to think about what this is asking and then run through the procedure. Now, we're not going to end up with a number, but we'll end up with a formula where we would get the right number of terms out. Let's talk about what's happening here. What's happening is we want to compare. So we have the sum, k equals 1 to infinity. That's what we're trying to find. And what we're saying is how many terms we have to go to. So we want to go to, not to infinity, but we want to go to some capital N, 1 over k squared plus 1. And we want to make sure that that number is less than 10 to the negative 5. That's what we're saying. So the question is, find the end where this is true. Now, there are actually infinitely many, because if you say, oh, if I add up the first million terms, that's enough. Well, if you add the first 2 million terms, you're still enough. Usually our goal is find a reasonable choice for n. Okay, so that's what we're after. That's what the problem is saying. And I think that's probably one of the hard parts about questions like this, to say, what are we asked to do here? Okay, so we're trying to figure out how many terms do I need to add so I'm close to what the value should be. Now, if we think about what this sum looks like, we say, oh, here I'm adding from 1 to infinity, but take out from 1 to n. So this says, look at the sum from n plus 1 to infinity, 1 over k squared plus 1. We want that to be less than 10 to the negative 5, right? because that's what happens when you take the difference here. So in particular, we're saying, at which point is the tail small? All right, so we're most of the way there. We have an idea. Let's sort of get a quick sketch of what's going on here. So we have our curve, 1 over k squared plus 1. We're going to think of our curve here as being, for the function, 1 over x squared plus 1. So here's 1 over x squared plus 1. And now what we want to do is we want to say, how can I compare the sum to the integral? And I want to do it in such a way to make sure that the sum is smaller than the integral. Because if I'm trying to bound the sum from above, it's like, okay, I want to find something sort of to squeeze into the gap. So what's going to happen? Well, I'm coming all the way up to n plus 1. And because it's decreasing, we say, you know, if we think of these as being Riemann sums, where we just use the right endpoints, then we can think of our areas here. These pieces, when we add them together, are the summation that we're after. So we say, all right, we can look at our picture and say, hey, this integral will be above the sum. But integral starting where? That's the key thing. Integral starting at what point? Well, the answer is starting at capital N. That's where we want to start. Because, notice, we're using our right endpoints, and so we should start here at our very first little Riemann piece fits in. Okay, so we say, aha, we now update, we say, look, the sum from capital N plus 1 to infinity of 1 over k squared plus 1 is less than what we would get if we integrate from capital N to infinity, 1 over x squared plus 1. Okay, so now we say, let's make this less than 10 to the negative 5. And if we can do that, then, because if this is less than 10 to negative 5, and our sum is less than this integral, then our sum is less than 10 to negative 5, which means we've achieved our goal. Our error is small. And now we're happy, because we have an integral we can actually do. The integral of 1 over x squared plus 1 is arctangent of x, and we're going to go from capital N up to infinity. And so, okay, well, when we plug in infinity, well, that means what happens as we go to infinity, we see, hey, this goes to pi over 2. And then subtract, well, arctangent of capital N. And that needs to be less than 10 to the minus 5. Now, we say, okay, what does that mean? Well, we can rearrange. We say, look, we need arctangent of n. So I'm just going to do a quick swap here. It needs to be greater than pi over 2 minus 10 to the minus 5. And finally, if we take the tangent of both sides, we say, look, for sure, if because tangent of arctangent will just be n, so for sure, if we let n be greater than the tangent of pi over 2 minus 10 to the negative 5, whatever that turns out to be, that's enough. That'll do it. And there we go. Now, of course, at this point, you got to go grab your calculator. And the thing is, you have to remember, hey, tangent has an asymptote at pi over 2. So you'll see, if this error is small, you're really close to that asymptote, which means you need a fairly large value for n. But we can say with complete confidence that as long as we've picked n a larger than that value, and we add up that many terms, then we are very close when it comes to finding an approximation to what it actually would be if we were able to add up infinitely many terms. So that's how we can use the integral test to help us do error approximation. Good stuff. Wonderful. All right, well, thanks for hanging in there. These are fun problems. I hope you enjoy it. I will say that among our tests that we develop, the integral test is a beautiful idea, but will be used somewhat less often in that the big thing from the integral test are p-series, which we didn't do much with p-series today, but we will see lots and lots of p-series. So make sure you remember what they are and remember how to use them because they're making a comeback. More tests to learn, more things to practice. Keep working on it, and hope to see you again. Bye.